Participants, let's start over, and yeah, I'll try to share the MATLAB window so that you can see both the presentation as well as I'll stop sharing this and share the desktop instead. I hope you're able to see the MATLAB window as well as
Yes, sir.
all right. So see, what are the essential things that we need to code this particular problem? So we need to have an idea of differentiation matrix first, right? So we need to have differentiation matrix. What are the things we need? Okay. So we need differentiation matrix and the collocation points. Okay. So what I do is I'll get these information with the help of a MATLAB file, shep.m, which you can take it from the textbook by Trefethen. It's available in that, so I have used the same directly. And what you see in the editor is the same Trefethen extract. Okay, so this M file is taken from that textbook. And you see that x is defined to be the collocation points caused by j by n, where j is varying from 0 to n, that is. And c is that constant. And for the diagonal entries, the same formula is used as I showed. I'll just take you to that. Yeah. So this C is either 1 or 2 based on what is I. And yeah, so for the off diagonal entries, you'll see that number 9, line is being implemented. And for diagonal entries, it is not the same as shown in this equation number 19, but rather an identity is used here, a relation. So in this spectral matrix, what happens is that the diagonal entry is the sum of negative sum of other entries in that particular row. Okay. So j going from 1 to n, j not equal to n. So all the off diagonal entries, you just add them, and your diagonal entry will be negative of that. So that particular relation is used in writing the diagonal entries. All right. So that is done. So let's now continue and see what are the things that we want. So remember, this function returns both differentiation matrix as well as collocation points, and we will take them as output of this function. Okay. And yeah, our main function, SLM function or SLM M file. So for SLM, what are the things that we want? We need to decide upon what is n, right? and the scales. N is the number of collocation points. And I mean, you don't have to decide because your shape.m will have some information on. Oh, it is yeah, it is to be passed because it is taking n as the input argument. Okay, so you need to decide on number of collocation points, and if it is not -1 to 1, you'll have to use appropriate scales. What do you what else you want? You need to decide on the number of terms that you want to add, like number of corrections. That is known as order of SLM, you can say. Okay, order of SLM or the stages of SLM. Okay, and what else do you need? You need you need to define what are the parameters that appear in the equations. Like in this case, there are some fluid mechanics parameters like porous parameter, viscosity ratio, and all those parameters have to be defined. And other than that, you need initial guess, okay? Initial guess, which is V naught of Z, right? So you need all these things to be defined. And how do you loop? You set order to outer loop. You vary the order, like first each term will be added, like when you fix order to be, let's say, 5, then you will have to have an inner loop which repeats 5 times and adds V1, V2, V3, V4, V5. All these corrections will be added to V0. Okay. So when you fix order as 10, then 10 terms will be added. So order you need to fix as outer loop, and I mean vary in the outer loop, and there will be an iteration variable that will be varied to add each term or each correction at the particular SLM stage. Okay, so that's the outer loop, and the inner loop will be on let's say iteration. So each correction is added here. Okay, in the inner loop, and we will try to plot our solution at each iteration and see how it is getting converged to. And in the inner loop, what are the things that you need to define? You need to define like the matrices. I mean, in this case, you need to define A and define the right hand side vector. What was the right hand side vector? It was B, right? Yeah, A n minus 1 or A n minus 1 and B n minus 1. Okay, so these are the two things that you need to define and add and you obtain the solution Vn just by inverting an minus 1, multiplying that with bn minus. So yeah, so this is all what you need in order to code this simple problem. So now let's get started with the new so I have chosen a script file. I'll just save this. Save it as SLM. Yeah, so it appears in the same folder. So what is the first thing that we need to have? We need to define number of collocation points. So let's say it's 20. So I'll just write in comments. Okay, so that's line number 1. So what else do we need? We need scale, right? So we need to define our interval. So what is A? So A is minus half and B is plus half. So this is the domain or ends of the domain. And N is the number of collocation points. How many number of points that you want to take? Yeah, so our scale uses this A and B. So scale is, as I mentioned, it's 2 divided by B minus A. Okay, that is defined. And then what we do, we just call Chebyshev function, which I showed earlier. So I'll call this Cheb and pass this n. So what this will return? This will return both the differentiation matrix D as well as the collocation points X. So we'll just put it like this. So once this line is executed, you have the matrix, spectral matrix saved as D and X. All right, so that is done. So we have our D. So we have D, we have X, we have N, we have scales, and we will define what is called as the scaled matrices. Okay, so scale, I'll call that as D1. So D1 will be just equal to scale times D. And if it is a second order derivative, we need square of this, right? So the square of that will be just scale times D1, you can say. So this is for the second derivative. So you can say this is first derivative and this is the second derivative. All right. So we will have to define the relation between independent variables. So I'll define Z to be the variable, new variable, which is the old variable, because in this case, X will be running from -1 to 1. So Z and X are related as one of the relation that I showed, straight line equation, B minus A divided by 2 times X. So if you want, you can put a bracket there. Plus B plus A by 2, I suppose. So that defines the relation between the two variables. And yeah, so you fix the order. So I'll say order going from, I'll run up to 10 orders. Like first order means the stages of SLM. Okay, so you keep adding one term, like V0 plus V1 will be the first order solution, we can say. V0 plus V2 will be V0 plus V1 plus V2 will be the second order solution. So like that, I'm considering up to 10 terms being added. Okay, so that is order loop. That is the outside loop. And in this loop, we'll just define our parameters and the initial guess solution. Okay, So the parameters that that involve are yeah, sigma square. I'll call that as S or small s. So S is for sigma. Okay, so sigma is let's say some 10 or something. So it's an inverse Darcy number. So it can have values from 1 to 100 or something. Okay. So that is S, and what else do you need? You need that lambda, which is viscosity ratio. So that also appears, if you see, that lambda appears as coefficient here in equation number 14. So that has to be defined. I'll take that to be 1. It's usually 0.8 to 1.2, that range you can take. And what else we need? We need the value of Forshammer number. F is equals to, let's say, 0.2 or whatever. Okay. So it depends on what kind of problem that you are dealing, and based on the physics of the problem, you will be able to decide on these parameter values. Okay. So I'll just say these are parameter values. So that is covered. What else do we need now? Parameters. Initial solution. Okay. So since it's as I mentioned, the solution is of the parabolic type, I'll use a parabola to be the initial approximation. So I'll just define initial guess now. So I'll call V or small v, or let's say big V, let's say Vm, I'll call, or Vm or Vn. So Vm equals to, so what will be the V naught if it is a parabola for minus half to half, and we assume that it will have a maximum velocity at 0 at 1. I mean, the maximum velocity of 1 at 0. Okay. So if that is the case, you can just take it as 1/4 or half minus z square, or 1/4 minus z square. Yeah, at 0. Yeah, at the extremes, it will satisfy the condition. Okay. And yeah, the maximum is not at the maximum value is not 1, but it would be 0.25. Okay, so let's use this as initial solution. 1/4 minus z square. Then what is the first derivative of this initial solution? It will be minus 2z. I mean, you should be careful. These are vectors now. You will have to use point-wise, I'm sorry, element-wise operator. That is dot. All the operators should be preceded by dot. The dot operator indicates that it is a point-wise operation. Otherwise, MATLAB can give you some problem of dimensions. Okay, and second order derivative is also required because our differential equation is of second order. So this will be 2. Yeah, I mean, here it's not required. This 2 is a scalar, so it can be just 2z, and here it's just -2. Yeah, those information is there. Initial guess information is there, and you just have to plot and start. Yeah, before you plot, you have to start the inner loop. So inner loop is just for adding each term in the sum. Okay, so I'll start an inner loop for IT. So that iteration will be set to order. Okay, or it should be starting from 1, I see. Yeah, let's set it to, oh, this is not required. Yeah, IT running from 1 to iterations, IT equal to 1 to order. Okay. And what you do inside this, you just define your matrices and invert A inverse B, that will give you the solutions. So A inverse B in MATLAB, as some of you might be using MATLAB, so it is a backslash operator which gives you the result. So let us define matrix. So what is A now? So the A matrix, AN minus 1. So I'll call that as A matrix. So A equals to D2, second order derivative, multiplied with lambda, right? So L star D2 minus AN minus 1. So what is AN minus 1? Diag of what should be written here? So diag of what is the equation? Let's go back and see. Diag of AN minus 1. So AN minus 1, if you see, it is sigma square. Sigma square is S in the code, right? So that is S and 2F times VM. So in the iteration, one term is added at a time. So you don't see the summation, but the loops will keep adding that one, okay? So that is going to be S diag of S plus 2F 2 star F. What else? 2 star F of VM, that's, yeah. So that defines the differentiation matrix. The coefficient matrix is given by this, okay? And what else is required? So you need to define the right hand side. So I'll just use B. Oh, B is already used. Symbol B is used. So I'll use R for right hand side. So R is equals to what? So R is given by just F into Vn minus 1 square. So just use this particular. So or you could just take the right hand side of previous solution. So the entire thing can be taken as Ri. Okay. So let us write this UM2 so it's negative of VM2. It's the entire differential equation that we have. Okay, VM2, that is the second derivative. Oh, L times VM2. Okay, L times VM2 minus what else we have in the S negative S, correct? negative S times Vm and so it's just a nonlinear differential equation. So the right hand side, the it has been simplified to this form. Okay, so it has been simplified to this form. You could just take this to be the nonlinear operator acting on I mean the differential equation that involves nonlinear terms. Okay, so that will form the right hand side part of your matrix. Okay, so that is F times Vm square, right? F times Vm square. So that is done. So your R is defined, the right hand side vector. So simplification of that is shown as here. You could use any of that. Okay. So this one or whatever it's shown. Okay. Now this is if definition of matrices. Then you impose boundary conditions on this spectral matrix. So that is the next step. So I forgot to mention that we have to impose boundary conditions on this matrix. So the first row, what we do, we will use the left hand boundary condition. On the last row, we will use the right hand boundary condition. Okay. So it is going to be a n plus 1 all the rows, that is there are 1 to n plus 1 row, columns, that is. So an, that is nth row, all columns. So you could just write it as nth row colon. So this could be equal to the identity matrix. So in MATLAB, identity matrix is given by EYEI. Okay, so EYE acting on that's the last row of identity matrix. So EYE. So this will just be specific because we don't know the dimension of identity matrix. So let's mention it as 1 to n plus 1. Okay, so that is the last row that I was showing you. Yeah. So this one, I'm imposing it on the n plus 1th row. Like that, the first one should be also taken from the identity matrix. So that is A of 1 comma colon. So that colon represent all columns. Okay, if colon appears in the second place, it represent all columns. If it appears in the, I mean, you must be knowing some basics of MATLAB, or else you can just pick up using help easily. So this is going to be I of 1 comma 1 to n plus 1. All right, so this is done. So, and correspondingly, the first element and the last element of the right hand side vector should be replaced by 0. Okay, so how do I do that? R of n plus 1 should be replaced by 0, and then R of n should be replaced by R of 1 should be replaced by Z. All right, so this imposes boundary condition on this matrix. All right, and all you need to do is just invert it. So when you invert, I'll write the solution as SOL. So solution is A backslash R. So it's A inverse into R. R is the right hand side vector. So you have the solution at all the grid points. Now this will have the derivative information also. So you need to extract the solution and the derivative and the second derivative. So how that is done is with the help of like first n plus 1 values represent the values of the variable. So we will define that Vm equal to what's happening here. You should tell me. So sol 1 to n plus 1. Okay. Yeah, first n plus 1 values. Vm1 will be equal to Vm1 plus sol n plus 1 to 2n, or you could just use the differentiation matrix if you are okay. So just use the differentiation matrix D1, multiply that by Vm, that will define Vm1. Okay, so in instead of yeah, then Vm2 is the second derivative. Just differentiation matrix multiplied by this vector will provide second derivative. So what's happening here is the current solution, like the correction at the nth stage is being added to the old VM. Okay, so it's overwritten on that. So if you start with some initial solution, so the correction is being added on to that. Okay, so the SLM addition of each term is happening at line number 29. Okay, so the SLM corrections are being added here, one at a time. Okay. All right, so that is there. So all these variables are defined. So we'll just close the inner loop. Before we close the inner loop, what we can do is just plot the results. Okay. Or no, after the inner loop is done, we will plot the results in the outer loop. Okay. So I'll use pause command. So it will ask for a key in. That means it will wait for us for a while. So plot x, yeah, plot z comma vm. So we will plot the initial solution also when it was defined. Okay, so it was defined here outside of this inner loop. So I'll try to plot that here too, not there. Yeah, plot here, and we will hold on to that particular plot. So on the same plot, we will try to plot the successive corrections that we made. So that is, you can hold a plot using hold on command. Okay. So that is plotting the initial solution. Now, after the inner loop, you're plotting the successive solutions, okay? And then you just have to end here, okay? And let's try it. Our code is ready, and whether it runs or not, let's see. So it should be order equal to. So if there's any error, we will try to debug it. And if we are lucky, we may get the solution here. So let's see. So yeah, there is some error. So line number 22, it has plotted the initial solution. As you see, the maximum velocity is at at 0, which is 0.25. But R, there is a problem. So what is the problem here? I think we should use a dot-wise, point-wise, or element-wise operation here. So dot star should be used. And there is problem here too. Size inputs must be a scalar. So or we will define some matrix I, and then we use that because the definition is not available here. So we'll just define I. We will define the dimension of this. This I is identity matrix of order n plus 1. Okay, so that will resolve the problem, I suppose. Yeah, so it's paused now. So I'll oh, there is some error. Maybe it's error in this particular yeah. So I'll just so it's minus L into VM2 minus VM and then minus F into VM square plus there is one plus 1, I suppose I missed out. So there's something else. What's the differential equation? Let's see. The starting one, which has
Hello, sir.
Hello.
Yeah.
Sir, I think there is a typo mistake when you defined D2 equals to scale star D1. It should
It
D
should
square.
be. No, it's fine, right?
For second derivative, D1.
So, yeah, D1 is the first derivative, so D2 will be the second derivative. I don't think that is a problem. I think problem is somewhere here. Other thing seems to be all right. Can somebody figure out what is the problem that we're facing here? Maybe the values are fine. L is taken as 1, S is 10. Let's take S are also 1. And this to be a small number. Is this fine? PA. Or let me just open one of the code that runs. Let's not waste time here. So this is how you implement. So I think I made somewhere an error which is causing this. I'll just open a program which is running. I'll just show it to you. Okay. So yeah, so here, I missed out this particular term, which is the identity, which is the constant term. I missed out on the constant term. Yeah, let's add that term here, minus I. Just a second. Sorry about that. I think I'll have to quit this. Yeah, I'll just run that code which runs and perhaps share the same thing. You could go through and find out what is the error. Yeah, this is the running code. I'll just run it and show it to you. So I'll just use pause command here. See, as you can observe, this black one is the initial solution. The red one is the first correction. And you keep pressing the key, you see that the color of the second curve is changing, but it has already converged. After second iterations, it has already converged. So I'll run it once more and show it to you. Yeah, so 10 iterations I'm running. So that's the reason. Yeah, I'm just enlarging the, yeah, you see after second iteration itself, you'll see that the solution converges. Okay, so we will come back to this code when we have to. And this is how you can easily implement. The implementation is easy because all you need to do is define your matrices properly and impose the boundary conditions. See, I have taken a simple problem. So that's why you're seeing one matrix. So you could see blocks of, this A to be formed of blocks, different blocks corresponding to different variables if you have a system of differential equation. Okay, so that is what one thing that changes. Otherwise, the structure of the code will be like how I showed to you. Okay, so you'll have to define in accordance to whatever I indicated earlier. Okay, so yeah, so let's go back to our presentation. Yeah, so we'll now discuss some of the convergence results. Okay, so we assume that the nth order solution by SLM to be Vn star, it will have n corrections added, right? So n corrections added to V naught. Okay, starting from V naught, you have been adding n corrections. So that is the nth order SLM solution. It's denoted as Vn star. Suppose V star is the solution, required solution, then your error at the nth order, the nth stage, can be defined to be a 2 norm like this. And how do we define convergence rate? If this limit exists, and if it is equal to m, then this p will be said to be the convergence rate. So this is error at the n+1 stage. This is the error at the nth stage. And if the error at the n+1 stage is proportional to pth power of error at the nth stage, then we say the method is of converges at a rate of p. Okay, and this m, we don't have any idea about m, so you could eliminate by taking successive ratios like this, and your p can be obtained as ratio of log terms. Okay, so I just show here that p is calculated for different n values for three different initial solutions. So this is a non-smooth solution, which is of triangular shape. Okay, so even with this non-smooth solution, you could achieve a nice convergence. You'll see that this number p is somewhere around 2. So which indicates that it is of second order convergence. Okay, and that's because it's based on Newton's method, and you're dropping the linear term. So this is what is quite expected. So you're following linearization, and it's something like Newton-Raphson, which has a second order convergence. So, I mean, if you see this particular solution is a very close solution, like for the nonlinear problem. So it is a very better approximation among the three solutions, and it will converge at the first level itself. Okay, yeah, we will now talk about this dependence on initial solution. Yeah, even if you have a non-smooth approximation, which is very far away from your actual solution, it will converge in not more than three terms or three iterations. So I'll just show that using the code I have in the other code. So I'll just comment this one and uncomment the non-smooth solution, initial solution. So let me, if the figure file is open, let me close it. So I'll close this first. So it's around 0.6. So that's your first solution. I mean, the zeroth solution. First correction. That's the second correction, purple one. So thereafter, you'll see that the curve has been changing the color, but it stays there. That means the convergence has been achieved at third iteration itself. Okay. So even with the non-smooth bad initial guess, you could see that it converges. And I'll just show one more initial guess, which is very nice approximation. So this is a very bad initial approximation, but even in that case, we saw the convergence happen quickly. So I'll show with the best initial approximation that we can have for this particular problem. And let me close this particular figure. And let's change the axis to be somewhere around point. All right, so this is the initial approximation, which comes from this particular function. Okay. And yeah, I have it on the slides also. So I'll show it using the code. So So it's the first level, I mean, the color is changing, but it stays on the black one itself. So it's almost converged in the with one correction itself. Okay, so that's a best solution. So one correction itself gives you the, and I have shown here some error plots for 3 different types of initial solutions. Rather two different types of initial solution. One is parabolic and the other one is a cos hyperbolic thing. And this is in the absence of nonlinear Forchemer term. Okay, so this is for the in the analytical solution of the Darcy problem. Okay, so if the nonlinear term is absent, so it has a analytical solution like this. And you see in any case after 5 iterations, the error is almost 0. I mean, it's 10 to the power minus 50 or something. Okay, so it is observed for all different choices of parameter values. Okay, so what does this indicate is the method does not depend on the values of the parameters that are chosen. And it also does not depend on the initial solution, as I showed previously. So however bad your solution was, it was converging very I mean, if it is a bad solution, bad initial solution, it would have taken more iterations, but it would have eventually converge. So it is insensitive to the initial solution. At least for this particular problem, I can say that. Okay, as I have shown using the plots. I mean, yeah. Okay, so that is concerned with solution of BVP. Now we can, I'll just share the presentation only. Yeah. So now how to deal with initial value problems? I think I'll have to wind up quickly. I'll take 5 more minutes if it is permissible. Can I continue for 5 more minutes to wind up?
Hello, sir.
Yeah.
Yes, sir, you can continue.
Okay, thank you. So how can we handle IVPs? So initial value problem, let's say you have the domain 0 to t naught to tn, and you know the solution at this particular point. And assume that your solution has some chaotic behavior, like it varies abruptly over small intervals. In that case, your SLM does not work as it is. Okay, it cannot handle these small variations. Okay, if it is an IVP whose solution goes very smoothly, you could just do away with the one interval, just solve it something similar to how you done your boundary value problem. Okay, but in this case, it so happens that when your solution varies abruptly over small intervals of the domain, then the original SLM can't handle this. So what we need to do is have to go for multi-stepping version. That means you will have to take small intervals, okay, T1, T2, and so on. and solve the problem over each interval. So solve in the interval T0 to T1, okay, and solve the same problem in the interval T1 to T2. So when you keep solving them, what you need to do is you have to glue the, when you solve it over T0 to T1, you will get that part of the curve. Okay, when you solve it from T1 to T2, you get the another part. You just glue the solutions at that particular internal knot. So we use such technique when we use interpolation, that when we do interpolation, right? So we use such a technique. So we glue the solution at the internal nodes, that is. Okay, so with that, it's easy to handle initial value problems with chaotic nature. So something like Lorentz system, I should mention, has that chaotic behavior. Okay, so which is also coming from a fluid mechanics problem, and basically it was I mean, it was Lorentz who derived that particular system, and it shows very chaotic nature for some particular value of scaled Rayleigh number. Okay, so SLM as it is cannot handle. We'll have to use the multi-stepping version of SLM. So that's how you can handle IVPs. And for handling boundary eigenvalue problem, okay. So let's take a problem of this kind: d square y by dt square plus lambda y equals to 0, and y of 0 equals to some 0, y of a equals to 0, so some condition, okay? So y of b equals to 0, like this. So if you see, you have homogeneous boundary conditions and a homogeneous differential equation. And as a result, what happens is that this will have this lambda, which is called as eigenvalue, controls the existence of nonlinear, non-trivial solution. Okay, so the non-trivial solution depends on the value of lambda. It does not. In a homogeneous differential equation subject to homogeneous boundary condition always will have a trivial solution. So if you want a non-trivial solution, it cannot happen for all values of lambda. So it happens for some particular values of lambda. Those are called as eigenvalues. So some problems in fluid mechanics are such that you will have to estimate this eigenvalue along with the corresponding eigen function. In that case, your SLM can be easily used to handle the eigen boundary value problem as well. So what you could do is treat this as an additional variable. Okay, so if lambda is treated as an additional variable, then lambda y can be treated as a nonlinear term. Even though it's a linear problem, you can treat that as a nonlinear term and use successive linearization method as you did in case of BVP. So having said that, when you treat lambda as an additional variable, what happens is that for closure, you would require an additional condition. So for that, one could use normalization condition, something like y prime of 0 equal to 1, okay, because it's a second order. So I can only mention either. Okay, y of a, that is, okay. So you could treat this as an additional variable. Okay, so y and lambda are the two variables that you are solving. Okay, And to cater, I'm so sorry, participants, of the background noise. All right, so let's finish it off quickly. So you need an additional condition, as I was mentioning. So it's because of closure, and that's how you handle boundary eigenvalue. It's otherwise you can just use the same way as you used SLM for BVP. Same thing you can use. So just use this additional modification of introducing some pseudo differential equation and a normalization condition. Okay. All right. So how does it compare with shooting method? I was planning to brief about shooting method if I had some time. Unfortunately, I don't have much time to talk about shooting method, but I'll use just comparison between SLM and shooting. So many of you who are working on shooting, you'll see that shooting method is very sensitive to initial solution, right? And as a contrast, SLM is not so sensitive. As I showed with the help of different bad initial guesses, guess solutions, SLM was able to converge nicely to the required solution. Okay, so that is one standpoint of SLM, which in comparison of shooting. Okay, so yeah, with this I'll just list some summary of what we have seen. So successive linearization method has quadratic convergence, and it's not so depend on the type of initial solution that you have. Even bad guesses, it gives you guaranteed solution. Okay, and it's not sensitive to parameter values also. It captures boundary and initial effects effectively. So that is another thing what I should have mentioned here. Shooting doesn't that I mean it's not capturing the boundary and inertial effect that effectively. Inertial effects are not captured properly. Whereas here, SLM captures the same thing nicely, okay? And you can use multi-stepping version for initial value problems with chaotic behavior and slight modification of the same SLM for solving BEVP. And these are some of the references you can refer to. So this is the textbook that I was talking about. So it has many inbuilt, predefined M files, like that sheb.m that I showed earlier. So I took it from this textbook, okay? And Canuto et al. Is the other book. Weidman is the Weidman and Reddy are the other book, which is very good for spectral method. Okay. And yeah, the more details of this particular problem, you can find it in this particular book chapter. All the details, you can find it here. Okay. All right. With that, I come to end of my talk. Thank you for your patience, and I open myself for any questions.
You may check your chat box, sir.
Yeah.
There might be some questions posted to you privately.
Under Q&A,
There is one
yeah, chat, I see.
in Q&A. There is one question. I think it was during
Yeah,
your talk.
should VM2 have D2?
Hmm.
Yeah, I think it is D2 if you use matrix D. Yeah, if you use matrix D1, it is it's scale times D1. So it can be done in any of these two ways. Both are fine, okay? If you use the original differentiation matrix D, then use scale square times D square. So that is one way. Or if you use the first order, the matrix corresponding to first order, if you treat the second derivative as derivative of derivative, then this should also be fine. So that's what, oh, VM2, you mean? Oh, yeah, that was a problem, I suppose. Yeah. Thanks for pointing out. Yeah, that should have been, no. Yeah, if it is VM1, I think it's fine. This is fine. Yeah, if you use VM, then it should be D2. Yeah, same way as I told earlier. So this is fine. So you can figure out. I'll share the non-working code also. You can just figure out what is the problem and fix it. And you can use the same code to all. You can alter the same code, and once you have idea of SLM, can just edit this for other problems too easily. And any other questions? Oh, I apologize. There were some requests to maximize the presentation screen and all. I just completely ignored that. I apologize for the same. Yeah, there were some suggestions also. Sorry, I was looking at my desktop all the time and my presentation, and I was warned by the coordinator to have a look frequently at the chat boxes. I completely ignored. I'm sorry. Yeah. I don't see any other questions other than some suggestions.
Okay, sir.
Yeah.
So thank you very much for a very nice informative talk on spectral method as well as SLM, the hybrid
Just
method you have
one
used.
question. One question I see now in Q&A.
Okay. Please answer. Yeah.
Yeah. You discussed the spectral methods in MATLAB. Is it also possible for other softwares like Maxima and Mathematica? That is very much sure. If you can do it in MATLAB, you can do it in any other software. It's just different languages. Like, yeah, it can be done. I mean, you'll have to follow the syntax of that particular programming language and just have to convert the same thing there. I've given you the algorithm. So, I mean, you can use this as an algorithm and implement on the other softwares too. Yeah, that's possible. So if there are no more questions, I'll hand it over to the coordinator, Dr. Om.